Hello, and a very warm welcome to the web seminar series of LS Telcom. My name is Heiko Ross, and I will provide you with a brief introduction to this web seminar. Today, we're having the second of a two-tier web seminar series. The focus of the web seminar series is electromagnetic spectrum and how it can be secured, how it can be made available, managed, and controlled to achieve dominance in this crucial area of operation. Today, the focus of our web seminar is on LS Observer, its automated spectrum surveillance, DF, and geolocation capabilities, and how it provides situational awareness in combination with mySPECTRA, which we have seen already last week during last week's web seminar. Before my colleague Philip Abel will start with his presentation, let me please briefly introduce LS Telcom to those that may not know LS Telcom yet. LS Telcom was founded in 1992 in Germany. Ever since, the company has substantially grown, today counting close to 250 employees in 10 countries. LS Telcom nowadays represents a globally leading supplier of system solutions and consulting services, addressing the optimum use of the available radio spectrum to achieve mission success. As such, we deliver fully integrated spectrum management systems, automated radio monitoring systems as well. We also provide strategic spectrum consulting services and training programs. As such, we, for example, advise these days the European defense agencies in spectrum-related matters. Lately, we have also been more and more in touch with customers concerning 5G and how 5G can be applied within a military context, for example, as part of smart military bases. Until today, we have provided system solutions and consulting services to customers in more than 100 countries. Both our system solutions and consulting services are based upon global know-how and experience that we have gained throughout 29 years of operations. Now, let me come back to today's web seminar. The web seminar is scheduled for 45 minutes. After this introduction, Philip's presentation about the capabilities of LS Observer will roughly last 30 to 35 minutes, such that we have another 10 minutes for questions and answers. You may certainly post or ask questions during the web seminar using the chat window. We will answer as many as possible, as mentioned before, during the Q&A session at the end of the web seminar. The web seminar will be recorded and made available. You will receive an email with a link to a recorded web seminar tomorrow, latest on Friday. Now let me conclude with this introduction. Thank you once more for joining and hand over to Philip. Enjoy the web seminar. Philip, welcome.
Yes, thank you, Heiko, and welcome from my side. My name is Philip. I'm the responsible product manager at LS Telcom for our spectrum monitoring, spectrum surveillance solutions. And today I will present you this web seminar, military operations within a contested electromagnetic spectrum. And I will present to you today our automated spectrum surveillance system, LS Observer. Yeah, to start with what we as LS Telcom offer in the part of military spectrum surveillance, we offer integrated solution for electronic warfare, SIGINT technology, various ESM features like the detection and evaluation of electromagnetic emission, 24/7 full spectrum surveillance and recording, anomaly and enemy detection, localization then of emission sources, signal of interest demodulation, decoding and recording. We at LS Telcom offer various integration solutions, so we can do customized integrations based on shelters, tactical vehicles, or fixed sites. Also, we offer customized ECM solutions, so jammer technology. So to start with the LS Observer, what is LS Observer? LS Observer is our sensor-based automated spectrum surveillance system. What does this mean? So first, spectrum surveillance, also known as spectrum monitoring. Here you can see a screenshot of our LS Observer software, a typical power versus frequency chart where you can see all the frequencies. In this screenshot, it's FM. Down here, you can see a waterfall chart where you can see the signals over time. But LS Observer is more than this classical view. We have sophisticated features like AVD, automatic violation detection, where the LS Observer permanently compares the live spectrum with the user-defined reference spectrum. And in case of any anomalies, for example, an enemy emitter or some interference or other signals, you will be automatically alarmed by the system. And then you want to know where does the signal came from. LS Observer offers multiple features to locate a signal to perform direction finding. LS Observer is sensor-based. Here you can see our hardware portfolio of our smart sensors for different applications, so from fixed application up to portable mobile application and up to even flying application with our LS Observer airborne monitoring unit. You can, all the sensors you just see, you can connect together to one network, to one LS Observer network. Here's a typical example. So you have some fixed stations, some portable and some mobile equipment, which you can connect together and control from a central position, or you can even control from a portable equipment neighboring fixed stations, for example, via the network. LS Observer is a highly automated permanent surveillance system. So the LS Observer is capable to do permanent 24/7 recording of the entire spectrum of interest. So for example, 9 kilohertz up to 6 gigahertz. Then we have this automatic violation detection feature, so automatic detection of anomalies. Based on this, alarms are generated and the source of the anomaly can be detected and located. Yeah, as we saw in our last web seminar of this series, regarding the spectrum management world for defense. So we saw last time Spectra EMC and Spectra Plan as part of the mySPECTRA suite. So the spectrum management product of LS Telkom. This is for sure integrated seamlessly with our LS Observer system, yeah, because spectrum management and spectrum surveillance or spectrum monitoring belong together. Yeah, if you only know the theory from spectrum management, it's not good. You need to look at the reality. You need to know if your database is correct, if there are any anomalies in the reality. You can also do with the LS Observer so-called reverse engineering. That means you can build up a spectrum management database by using the monitoring. So that means you come to a new site, apply some monitoring units, do permanent measurement, and then look at all transmission which are on the air and put them in a database. So we have this interface to mySPECTRA. So the LS Observer gets information from the spectrum management, so the frequency allocation, information about which frequency are used by civil on the civil side, by LEs, by the hostile frequencies. Then you get station data, and all this data the monitoring system can use to have a reference baseline to know what is the theory, and in case of any anomalies in the reality, it will automatically trigger you an alarm. So here you can see the inside of our hardware, our remote monitoring units, whether it's portable or mobile unit or fixed unit. So there's always a receiver or two receivers included, embedded processing power, a modem for network communication. And what is important, all of our unit has a large internal storage. So That has the advantage that you can capture everything at first locally. Everything, I mean, for example, 9 kilohertz up to 6 gigahertz or even 18 gigahertz. So you don't need a permanent connection to a central database. So our sensors can independently record the monitoring data on their local storage, and later you can back it up either via the network or via putting an SSD plate to it and loading it to the central server. Here's an example. I just mentioned it. We can also integrate two receivers in our monitoring unit. What does this has for advantage? With this, you can do parallel tasking like illustrated here. So the first receiver looks at the wideband permanent spectrum, like from 9 kilohertz up to 6 gigahertz, and does the AVD. Once there is an anomaly, the second receiver can tune on this anomaly and can, for example, do a signal of interest demodulation or decoding, or can do a geolocation task or direction finding task to locate the anomaly source. Yeah. Also, we can do with the second receiver, which is a unique technology of LS Telcom, do the DF time travel. That means you can do a wideband recording of the so-called directional spectrum. With DF time travel, you can do direction finding based on stored data. We will later see the details on this. What you can always do with LS Observer, due to this unique storage technology, you can always do analysis on stored data. Not all the data. You can also, as a user, filter the data on the monitoring unit. You don't need to download the full spectrum. You can only download what you need, a portion of it in time and frequency, and then you can do rich analysis features like classification of emissions, direction finding, or geolocation based on stored data, only to mention this as an example. Details to our hardware. We have here the fixed monitoring unit for permanent outdoor or indoor application. It's withstands really a lot. It's worldwide in operation, I would say, in really extreme zones from a climatical point of view. We have this in Indonesia and Middle East and Finland in operation, for example. It can be really flexible installed, like you can see here in the middle on just a lantern pole in a camp here, or just on a building roof, or like we see here on the left side of this, our demo system in Germany, just a self-supporting mast here. Then a bit more mobile form factor is the transportable monitoring unit. It includes battery up to 8-hour runtime. With this, you have two applications. One application you see on the left side, you can put it on the vehicle and have a mobile measurement system, but you can also put it and use it as a temporary fixed station, like you see here on the right side for spectrum inventory. Yeah? Like if you come to a new site, you put it at a certain location, measure for 1 week, it captures your all transmission which are active during this time. You can fill up a database with this, and then put it to the next location and do it again, and then you have a reference baseline for permanent surveillance. Yeah, you can also use it for temporary fixed surveillance. You can put, for example, 3 of those units around your site, and can then also perform, for example, time difference of arrival geolocation to locate an emission. Then this portable form factor is our PPU protected portable unit. It's ruggedized IP67. It also has the 2 use cases. You can close it and use it for permanent measurement. So for temporary fixed measurement, it will automatically record everything. You can also put it to the network, or you can directly, for in-field measurement, directly control it via the embedded display. It also includes batteries up to 3 hours runtime. It can be extended with an additional pack up to 8 hours. Then for in-field application like emitter homing. We have our LS Observer PMU portable monitoring unit, and here on the left side you can see the application emitter hunting, it's called. So you have the PMU based on a backpack system, you have a handheld antenna, and the LS Observer CMS software guiding you towards an emission source. So with emitter hunting, also called homing, you try to locate an emitter source on the last meter by using a handheld antenna. And here's our newest innovation for this. On the roadmap for this and next year, we couple this with data classes. And here you don't need to have a screen anymore. Yeah, with the data classes, a dedicated view for the homing is directly projected to your eyes. So you can see this data screen, but you can also keep your environment inside, yeah, in parallel. So you can always look in front of you, but you can also see the data screen. And the advantage of this, it includes a camera, so it can live broadcast the camera picture to the emission control, for example, also the data screen. And the person who does the homing can also get a remote guidance by an RF expert to do the homing. Last but not least, our flying observer, everything which stands for LS Observer based on an integrated drone system. With this is interesting, if you fly up and perform a measurement, you suddenly see signals appearing in the spectrum, which you do not see from the ground because you can overfly any obstacles, any artifacts from metal structures. So you have a really clear view in the air. You will increase the coverage area. With this, you can also do direction finding. We have a directional antenna, so you can turn the drone and then get a line of bearing from the software. Also, you can fly into microwave links with this, which can for sure not be measured on the ground. And that's why we also have a model up to 44 gigahertz, either your own or enemy microwave links where you can do analysis in it. Then we offer our own, as LS Telcom, our own automatic direction finding system, the unique AOA1XX system. And now we come back to the DF time travel, which I already mentioned. This system this system can perform direction finding not only live as usual, but also based on stored data. And this stored data can be, for example, 9 kilohertz up to 6 gigahertz. And within this frequency range, you can select any signal and perform direction finding for it. That means you can, for example, look back 1 week at the in time in the recorded data, and you can do direction finding even if the emitter isn't on air anymore. Yeah. Further, this system can do direction finding with only one antenna from 8 kilohertz up to 12 gigahertz, depending on the version. And we also have an 18 gigahertz version, which can do direction finding only, and the 12 gigahertz can also do omnidirectional monitoring. Yeah. This system is able to receive H-pole as well as V-pole signals. It can perform co-channel signal resolving if you have multiple signals on the same frequency. We have the so-called directional monitoring mode. I have a few slides later to describe you to this unique feature. This antenna system can be used for fixed or vehicle-based operation. For fixed application, it's also available with a lightning rod. So here you can see some example here on the left side, a fixed installation on a rooftop, on the right side on a Toyota vehicle and a mobile application with this antenna. So how does it look like, the DF time travel? I told you, okay, you can do this live, but what it's unique about it that you can do it on stored data. And here it's we are in the LS Observer CMS software. We load a stored data set from 10 megahertz up to 1 gigahertz. We zoom in to pick up a signal, and we just double click on this signal, press analyze, save evaluation, and then you see it calculates you a line of bearing. So you have now one line of bearing, then you can drive to another location, or you can load a data set from a different location, analyze or let the software create a second line of peering, and then you have a cross intersection, a triangulation. You can locate the emitter source, and this all possible based on store data. Like you can see here, from 10 megahertz up to 1 gigahertz, you can pick up any signal and do this direction finding like we just saw. So I just mentioned as a unique feature of this system, the co-channel signal resolving. In the situation like you can see here, if you have multiple signals on the same frequency, like a friendly signal and a co-channel hostile signal, they cannot be separated in the spectrum from omnidirectional view. With our antenna, you can separate multiple emission sources, so you will get 2 line of bearings. If you do the triangulation, you will get 2 hotspots. That means 2 triangulation results, like we can see here on this illustration. So, for example, that this hotspot is then the friendly communication, and the other hotspot is a hostile interferer. So you can see, okay, I need to go to this hostile interferer and take this out. Then the directional monitoring mode, another feature of the AOA1XX DF system, as it consists out of multiple directional elements in multiple layers, partly also log periodic antennas. Just to mention this, without any rotators inside, so no mechanical problems. With this mode, you can pick up any of these directional elements and can perform monitoring on it. By this, you have an enormous increase of sensitivity, gain, coverage towards a certain direction. So you capture a certain azimuth by this. Like you can see here on the right illustration, if your hostile signal is on this side here, you can focus on this. You increase in comparison to an omni element the sensitivity. So you can, for example, do signal of interest analysis and demodulation, which you won't be able to do with omni element. Also, if they are on the same frequency, like you can see here, there's some small signal inside a wideband signal. You can focus either on this signal or on this wideband signal, which I called here the friendly signal. Yeah, and as we are in this example, we are at the border from Germany and France. You can see it can, one use case could be border protection. So you can see everything which comes from outside the border into your country, and from your country goes outside the border. Or you can do it the same for a site or a camp protection. And yeah, as I already mentioned, this use case, you can use it for the monitoring of co-channel signals. So you can suppress the co-channel signal to focus on only one signal. Yeah. Last but not least, for this system, you see our AOA system has a lot of unique features, but we will add another very unique feature in the future. LS has founded an artificial intelligence team who only focus on this part and will provide AI to different products at our portfolio. And one technology here will be AI-based AOA calibration. That means with this, we get an outstanding in-field accuracy. Normally, an AOA system is determined by the accuracy called degree RMS. For example, 1 degree RMS, it's a typical value, but this is measured in an open field scenario. So in a laboratory scenario, which has nothing to do with the reality. So in reality, you have a lot of artifacts like buildings, reflections from metal structures, mountain areas. You have a lot of artifacts which will lead to a decrease of the AOA accuracy. And with this AI technology, we consider this. We do a permanent recalibration in the field with this technology. How does it work? Yeah, for example, you're in the field with a vehicle and you have from surrounding metal structures, you have buildings. The car itself can be something which decreases the AOA accuracy. Then our AI calibrator detects that there is a direction error. How this is done with our LS observer, we can connect a known emitter database. So we have a database of known emitter around the vehicle. So for example, 50 kilometers away, a FM emitter, and then due to that, our system knows where the reference emitter is located. It knows, okay, my line of bearing for this frequency should be directly lead through this emitter. If this is not the case, you have an error. Yeah, for sure, this is not statistically meaningful if you only take one reference emitter. You take multiple emitters. Yeah, and the system also checks which emitters you can take. Yeah, which emitters has because we have the radiated power in the database, our system do wave propagation calculation and looks, okay, which emission can be received at the side of the DF vehicle, which signal can be used for the calibration, and then the AI does the calibration. It eliminates the DF error, and you have a really precise and outstanding in-field accuracy with our AOA antenna, and this calibration is done permanently. Okay, now coming to our system integration solution with LS Telkom, we are really experienced in doing customized solutions for military. You can see here some examples. So we do vehicles, we do shelters, from inside and outside. We put on heavy antennas like this here on the right side, this ECM jammer system. Then just to sum up what we can provide at LS Telkom, we can provide ESM and ECM solution. We do the modification, customization of tactical vehicles of any suitable type. We modify and create military standard shelters. We integrate all the measurement equipment. It must not be mandatory from LS Observer. We also integrate third-party measurement equipment. So we integrate then operator workstation, equipment racks, big telescopic masts for antennas. So the antennas, including rotators, all the powering generators, air conditions, and many more. So we can really flexible create all those things according to your needs. Now, away from the hardware to the LS Observer CMS software, you already saw a video for the DF antenna of this software. The LS Observer CMS central monitoring software is the one software which can control either one single LS Observer device, but also a complete network of hundreds of devices, for example. Here you can see the software view. We are now in the monitoring system overview where you can see all your connected stations, so all your network stations. And if you can see them also on the map. And if you want to start a measurement, you're here at the measurement control. You can manipulate the measurement, like adding here maximum hold curve. You can zoom in, you can do analysis. If you now want to look at the permanent recorded data, you go to monitoring data, load a recorded data set like this, and then you can scroll in time and focus on a certain signal like this suspicious signal here. Yeah. Now we load another measurement. You can either load as a user a complete measurement, or you can limit it in frequency or time. Yeah. Now we have a special illustration here, spectrum occupancy measurement, where you can see the utilization of the channels over time. Red means 100%, so there's permanent, this channel is permanent in use. Going to the bluer colors, it means there's a low occupancy, and white, there's no usage. Yeah? And here you have a nice example. On the left side, there's a lot of red, there's FM. On the right side, you have the ATC frequency, where only sometimes pilots speak, sometimes towers speak. And this was a measurement overnight. So you can see here from the evening hours into the night hours that the air traffic is reduced, and that the occupancy will increase again at the morning hours. Then to the automatic violation detection feature, I already introduced it to detect anomalies automatically. How does it work? So the user can define for each channel a mask. Yeah, he can define, okay, in my channel I expect a certain signal, or I do not expect any signal. Once there is a signal popping up in the channel, I will get an alarm. Yeah, if I expect here a signal, if I use the channel by myself, I can say, okay, that's my expected level, and this signal can fluctuate inside the upper and lower tolerance. Once it will get over this tolerance, you will get an alarm. So upper tolerance can be, for example, interference or another emission on it. Lower tolerance can be that it is an emitter outage. And this you cannot do only for one channel, but for your entire frequency range of interest, in so-called AVD template. You can see here, I have an example. Two emissions are going over the upper tolerance. I call them as anomaly. And the other emission is inside the tolerance. I call it now normal emission. Yeah. This cannot only be done manually. Manually, it means a lot of work. Our LS Observer is capable either to spectrum management database to calculate those masks, to calculate also the expected level via wave propagation calculations, or you can take a recorded measurement, for example, a spectrum inventory with a transportable monitoring unit where you measure 1 week at a certain location. Then it creates you a baseline. So all the signals which were active during this week will be taken into consideration for the AVD. And once you measure again at the location permanently, everything abnormal from this reference situation will trigger an alarm. That's how it looked like at the software. So you load the defined AVD task. Now we have it for PMR. And you give the resulting AVD template a name, AVD log a name, sorry, not template. The AVD log is a recording of all those alarms. So you can later on, after the AVD analysis, or even if it's still running, you can see the alarm history. So when and at which channel an alarm happened. Those alarms, you don't need someone who permanently looks at the screen. We can couple the LS Observer CMS, for example, with the emailing system or an external alarming system. So you don't need someone who permanently looks at the screen and looks once there is any alarm. You will get informed via the alarming system or an emailing system. Then once there's an alarm, we want to know where does it came from. Yeah. And with LS Observer, we offer 3 different technologies to achieve this localization. The first technology we already saw, it's the AOA, so direction finding, where you can create multiple line of bearings and do triangulation. You only need for AOA to measure at 2 different locations. Then you have already 2 line of bearings and an intersection, so you can triangulate an emitter. But for this, you need a direction finding antenna, either our AOA 1XX antenna or a handheld directional antenna. Then we offer 2 further technologies which only need omnidirectional, small omnidirectional antennas. The first technology is called TDoA, time difference of arrival, which takes the time differences of an arriving wave at different measurement locations. Yeah, like you can see here, there's the signal. The wave arrives first this measurement unit, second this, and third this. And based on this time differences, mostly nanosecond ranges, we can calculate it back and can say, okay, my signal came from here. In CMS, you have this heat map application. Yeah, we can see it here. Have another screen video how this works. Simply double click on this signal, select the monitoring unit. For TDoA, you would need at least 3 monitoring units which can receive the signal of interest in parallel. Yeah. Then the analysis is starting, and you can see immediately you have a heat map view. Now we applied some rolling averaging, so you can see the heat map is getting better and better for this application. And you have a red spot here next to this emitter on our demo system in Germany. Yeah. As we can tune a bit here, also the color scaling. Yeah. As TDoA is sensitive to geometric reason and to the bandwidth of the signal. So the best with TDoA is that the signal is somewhere inside the polygon the sensor's opening. If it's near the polygon, it's also good. You can see it's a bit widened out. It is in TDoA. If it's far away, you would get not a precise point. You will get some kind which looks like a line of bearing. Yeah. And TDoA works perfectly for wideband signal, but if you have really narrow band signal, from a physical point of view, you have problems with this with the precision. That's why, as LS Telcom, we offer another technology based on Omni antennas. It's called GROA plus, gain ratio of arrival. And what does it mean? Here we not only we do not take the time difference, but the received level differences of the emitter. That at first sounds really simple. Yeah, we just look, okay, one receiver receives the signal with a higher level, the second receiver with a lower level. For sure, it must be nearer at the first receiver. Yeah, but if we would take only this, you would not have a good precision. Yeah, that's why we add this plus in this technology. And this plus means that again, we take our experience in wave propagation calculation to this. We consider any obstacles between the surge emitter and your receiver. Yeah, if you only take the power differences, any obstacles like only a building, yeah, if you have a flat area, or if a forest, for example, can make this to a non-precise geolocation technology. But if you consider those obstacles and the wave propagation effects, we made this GROA to a really precise technology and perfect alternative to TDoA. That's why we call it GROA plus. We add this plus with the wave propagation calculation. And this technology is like DF time travel. This technology can also be done based on stored data. So you can go back in time and do a geolocation based on stored data, like from 9 kilohertz up to 6 gigahertz. Again, we see it how it looks in the software. So we load a data set. Here we have up to 2.5 gigahertz from 20 megahertz, but we only want to see at 121 gigahertz. It's a megahertz. It's the ATIS emitter of the airport, so an ATC emitter, and we select roughly the area where we want to do the calculation, where we expect the signal. Yeah, this can be this must be really rough, yeah, because you only have an option. Can also be the whole world, but then the calculation will take long. And then you select other recorded measurement. For GROA plus, you would need at least 3 different measurements from 3 different locations. Yeah, and then the analysis is running and the calculation is done. And then again, you will have a heat map view, which can be a bit here fine-tuned in color scaling, that we see the details. If you scale it, you will now see the hotspot And you see, if you zoom in, okay, it's inside the airport. So this signal comes from this airport. Okay. Then the last point here to mention is that with CMS, we can also do signal of interest demodulation. The CMS has embedded demodulation for analog signal like AM, FM. But if you want more, we have the possibility, we have an interface to third-party decoding software from Bositec called GoToMonitor, and this GoToMonitor has a very comprehensive suite of various classifiers, demodulators, and decoders, like for VHF, UHF, HF, military decoders, SAT decoders, PMR, including Tetra decoders. So we have a really great suite to do this demodulation, and everything is seamless integrated into the LS Observer. With this, we also have on the roadmap our own classification technology based on AI. So like the AOA antenna AI technology, we also do this for classification. And on the roadmap, we have that with LS Observer, you can do by next year, you can classify up to 20 different modulation schemes. And the algorithm can also learn. Yeah, that's a great thing on AI-based classification, that you can adapt this to the in-field situation, so that the AI, the artificial intelligence, can learn from your in-field situation, can learn new signals, yeah, can adapt to this, and can later then again classify those signals. That's a great advantage comparing to classical system, that the AI can learn new signals and can learn the reception quality on site. So if you really have a bad signal to noise ratio, it can take this into consideration and give you really great results. So this is now coming to my end. Thank you for your attention, and I will now hand over again to Heiko for the question and answer part. So if you have any question now, just raise it in the chat. Are there already any questions?
Thank you very much, Philip, for this nice presentation. I keep my eyes here on the conversation of the meeting, but I don't see any questions yet. So let me see if there was a question earlier coming in. There's okay. Well, then thank you very much for Philip. Let me maybe also I thought it was quite interesting, your presentation about the observer and about the the applications. In particular, when you applied big data, artificial intelligence, and also automation to all this. Looking back a little bit back at big data, when you talked about how you can look back in time, can you give us a bit of more information about how much data you store and what kind of time frames you can cover with that? Is this? Can you tell us?
Yeah, sure. So I mentioned already the large internal storage of our monitoring units. That's why we have this storage, because our philosophy of the LS Observer is to permanently record everything, because you never know which kind of data you will need afterwards. So you have the maximum flexibility. You can go back in time and can do analysis on it. You can always do for sure backup to your central server, but on the local unit, the storage of the local unit, it's capable to store up to 4 weeks of the raw data, so the full information of the spectrum. We also offer compressed data type, like data without any noise signals, where we only capture the signal, or statistical data like spectrum occupancy data. This can be stored up to 2 years till the local storage run full without any backup. And we also have the capability to store the highest, which needs the highest data amount, the IQ data. Yeah, but the IQ data, it can take, for example, for 1 hour up to 1 terabyte. So this is a data we have with our LS Observer, some data buffer, yeah, where we can, for example, store 5 hours of IQ data, and then it can be backed up to the central server. Yeah, that's these are the possibilities of LS Observer. Yeah.
Okay. And then last question from my end. You also talked about automation, automated violation detection. I mean, in the end, you always have to have a reference against who you compare the measured signals.
Yep.
What could be the references? I mean, we talked about spectrum management. How this data could be used, but what are the possibilities there?
Yeah, so the reference could be a database, a database where you have the frequency usage of the civil side, frequency usage, for example, of your allies. Yeah. Also, if you have the information already of your enemy. Yeah. So you have everything in this theoretical database, and then the spectrum monitoring can get a baseline. Yeah, everything which is in your database, it can consider, and it can say to you, okay, this signal, for example, is a signal used by your allies. Yeah, that's a friendly signal, and this signal is used by your enemy. Yeah, by the hostile. Yeah. But you can also do it the other way around, which I already mentioned. If your database is not correct, or if it's missing something in the database, you can fill from the LS Observer, you can fill a database. If you see a signal, you can say, okay, this signal is new. I feed it back to the database and categorize it.
Okay. Thanks a lot, Philip. I was just looking again at the kind of questions. There have been a couple of questions coming in. There was one question about what kind of synchronized communication connects monitoring stations on the field for correct position finding.
Now we're talking about two things. So one thing would be the network, how to network the LS Observer units. The networking can be done on various technologies, from using the public internet secured via VPN, up to using private military networks. For sure, we are very flexible. We have TCP/IP technology in this network, so we are also experienced by using different private or public networks. And I think also one question for this is about the geolocation. How does the synchronization work? And so the synchronization works either via the network, yeah, and for TDoA, you can either synchronize via the network or via using from satellite systems the precise atomic clock from the GNSS signal. So you have this precise time reference.
Okay, thanks a lot, Philip. I just realized there have been a few more questions coming in, but we are running a bit out of time. So what I would suggest is we will take a look at your questions. We will certainly respond to your questions on an individual basis for the time being. Thanks a lot, Philip, for your presentation. And yeah, I would now continue with with the conclusion, more or less. We are slowly but surely coming to an end of this web seminar. And yeah, once more, I'd like to thank you all for attending. This was indeed the last web seminar of this two-tier web seminar series. Nevertheless, we are already planning for the next webinar series, and we will certainly let you know both about topics and times or dates in due time. Please also keep in mind that we have the annual Spectrum Summit conference coming up on the 30th of June and 1st of July. This year, the first time digital and online. Usually it's here at our premise in Lichtenau, Germany. This year we will have topics like the challenge of the C-band, but also 5G campus networks and how they slowly but surely find their place into different markets and also into the military market. So please check our website. We will have registration starting soon, and make sure you get your seat on this year's Spectrum Summit conference. Let me here also briefly thank you our training academy that organizes and hosts these web seminars. The training academy, as you may know, offers a quite comprehensive mix of training courses addressing not just challenges and opportunities in managing and controlling the electromagnetic spectrum, but also in specific topics such as, for example, spectrum sharing. And I believe in mid of May we have actually a spectrum sharing training course which you can book, which you can join, which you can access remotely online. So certainly a great opportunity to learn about spectrum sharing technologies. Please check our website and our web store nowadays then for up-to-date information. If you or any of your colleagues would like to see this web seminar once more, you may certainly access and this session to which you will receive a link in a separate email tomorrow. In this email, you will also receive a link to an online questionnaire. It would be great if you provided us with some feedback, because in the end, it always helps to have your feedback in order to plan for the next web seminars and make sure that your interests are also considered. If you have any further questions concerning LS Observer, which we primarily focused on today, please do not hesitate to contact us. We would be more than happy to provide you with further information about this system. Now, let me thank you once more for tuning in today. We would be glad if you kept in touch with us, whether directly via social media, follow us on LinkedIn, Twitter, or Facebook. I certainly hope to see you again sometime soon, whether it's live or whether it's within one of our online seminars, Spectrum Summit, for example. Until then, I wish you all the best, and most important, stay safe. Bye-bye now.